Right, in this lecture we're going to talk about the transformations, I'll call it the transformation of p-vectors and p-forms. My demonstrations will all be on p-forms since that is the way it's usually done in books and there's no point in confusing you, but the analysis is the same for p-vectors. Now p-forms are elements of the 0p tensor product space, right? So p-forms are 0p tensors. So we already know the answer to this question. We know how these guys transform. 0p tensors are simply expressible as tensor products of the dual space, right, where there's p of these guys. And those things are a map that take a bunch of vectors, v1, v2, v3, vp, and gives you a real number, I guess an element of the real numbers, right? This is an element of the real numbers. So we know how that works. And we know how those things transform. We fully understand that the basis vectors of these guys will transform according to the inverse transformation matrix, and the components of those basis vectors will transform with the direct matrix, because the components of a p-form, the indices are all covariant, and the basis vectors themselves are contravariant. If this is confusing to you, you have to go back to that other lecture we did many lectures ago, somewhere in the first 10, I think, where we discussed covariance and contravariance in great detail. But the point is that p-forms, actually this is supposed to mean, this is a substitute for the word transformation, right? I tried to make it short, but now it's confusing x-form and p-form, right? That's silly. So let me take that away. Transformation of p-forms. So p-forms, we already kind of know how they transform, right? They transform according to the same rules we learned a long time ago. Now the basis of this tensor product space, right? The basis, if we pick it, is going to be E mu tensor product E nu tensor product dot dot dot, say E gamma, and there's going to be p of these, right? That will be the basis of the tensor product space. So it'll be every possible combination of mu, nu, gamma indices, and it's going to be a lot of them. There's going to be, say, the dimensionality of, if the underlying dimensionality of V is n, then there's going to be n to the p power, n to the p basis vector. So the dimensionality of V is going to equal n, well, wait a minute, let me get this right. The dimensionality of V equals n. So the dimensionality of T0P is going to be n to the p. So that's a lot of choices. But since we're talking about p-forms, we know that this isn't right, because, well, we know that this is correct, right? That's the true statement, but we know that we're dealing with something totally different, because essentially what's happening is because it's a p-form, because it's totally anisymmetric, the coefficients in this basis tend to align in such a way that it reduces the number of basis elements of the subspace that the p-form really lives in. The p-form really lives in this subspace of the tensor product space. And by living in that subspace, it's got a dimensionality much smaller. Its dimensionality, the dimensionality of this thing, we know equals n choose p, right? It's n choose p. So that's a much smaller subspace. And because of that, the basis vectors that we need to describe a p-form, we're going to use these strict basis vectors, right? We're going to use E mu, wedge, E nu, dot, 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 wedge, E gamma, where mu is less than nu dot 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 is less than gamma. That strict basis, there's much fewer of them. In fact, there's only this many. And with that in mind, when we express a p-form in this basis, when we express a p-form, when we express this thing in this basis here, the transformation rule is different. It's no longer the standard transformation rule that we learned using these matrices. These matrices are involved, but they're not the same rules. And that's what we're going to study right now. All right, so let's use this as an opportunity too to review a bunch of different things. We may remember that this little thing I always draw, or used to always draw in the earlier part of this lecture series, is our space-time, and I would put down coordinates here, x0 and x1, and I always said, okay, x2 and x3, they're floating around there. This is to mean that every point in the space-time can be labeled with coordinates of some sort, and we know that that coordinate system exists, and we lay it down. For those of you who've completed the What is a Manifold series, you know all the mathematical structure you actually need to do this, and it's not trivial. But then we talked about how at each point in space-time we erect a special space, which is typically in the literature called the tangent space. It's a vector space that is at every point in space-time, and every vector space immediately creates a dual that pops into existence. And pretty frequently, in general relativity, certainly, there is a inner product on that vector space, and this happens everywhere in space-time. There's a separate vector space V and a separate dual space for that vector space V everywhere. And I think I was drawing it like this, the dual, right? And then I think we also talked about the fact that in order to get these inner products in every point in space-time, because every vector space has its own inner product, so you have to establish one in every place. And that was essentially codified by a metric tensor, G mu nu dx mu tensor product dx nu, which of course is a T02 tensor. And it exists at every point in space-time, so this guy here is really G mu nu of x, meaning it's a function on the space-time itself. And of course these guys are the coordinate basis. I don't think there's a hyphen in coordinate, right? The coordinate basis. And the coordinate basis comes back to the realization that V is populated by all differential operators generated by these basic differential operators, where for a four-dimensional space-time we have four of them, and each of these, of course, represents a differentiation by the coordinate function, the associated coordinate function. And the duals are in V dual, and that's generated by the equivalent one forms. We're now going to call them one forms because that's what they are. That's a new word that we didn't introduce them as one forms then, we just introduced them as the duals of these guys when we first talked about it. And we know that the mapping dx mu partial nu is the delta function mu nu. And the one-to-one mapping, so these were called the dual space, the dual basis to this, where this is what defines the dual basis, which does not establish a one-to-one correspondence between these two spaces. It seems like it might, but this is an arbitrary choice, right? And a one-to-one correspondence, the kind of one-to-one correspondence that matters is a canonical one that's forced upon us based on the things that we already have. This isn't a little arbitrary choice that's just convenient to define what these mappings are, but every single mapping exists inside the dual space. We just need a way to talk about them, and it's convenient to do this so we can talk about all the mappings. But it doesn't really say that if I pick a particular vector in V, right, one that's some linear combination of these elements, where the linear combination is based on the vector addition law and comes from the scalar bin of real numbers, which, by the way, also exists for this vector space. There's no way to take every vector in V and assign it a distinct, meaningful vector in V star, right? You could say, well, the vectors in V star are the ones with the same components, right? But that's just an arbitrary choice, again. So we need something that forces this connection. And we now know, of course, that what forces that connection is the metric tensor. Once we have decided on a metric tensor, right? Once we have decided on a, whoops, what have I done there? Once we've decided on a metric tensor, that metric tensor then drives a one-to-one relationship between these things. But this is an arbitrary choice. Well, I should say this is something we still have to add to the system. In other words, there is no canonical relationship between this and this absent a metric tensor. But once you have a metric tensor, then it does drive a canonical relationship. Okay, so that's where we were before. So now we're going to review a little bit about how tensors transformed, right? Remember, in every one of these vector spaces, these different vector spaces here, we also assume the entire construction of tensor product spaces, right? This has all the PQ tensor product spaces, and as a subset of those, you have all the exterior algebras of forms and the exterior algebras of P vectors, right? Remembering that these are both subsets of various tensor product spaces. So actually you would squeeze all of those things into these boxes as well. And again, everything is, each one of these members of these things, when understood to be tensors with, a tensor member of this tensor product space, we usually like to refer to as Q, and then it's some collection of P and Q indices, right? So it'd be P, it'd be Q, say A, B, C, D, but it's a function of space-time, right? The components of these things are functions of space-time, and in this case, I guess it would be well, that's backwards, right? Because I'm supposed to have the forms first, right? No, that's right. This vectors first. B, D, X, C, D, X, D, like that. And these things are function of space-time, so again, these tensors are tensor fields, right? So, let's see. So we know how these things transform, right? We've learned how to transform tensors. And the rule for transforming a tensor went a little bit like this. Let's take that one we just did. Q, alpha, beta, gamma, delta, partial alpha. We'll use the coordinate basis. There's no reason to use the coordinate basis. I could just use the abstract basis if I wanted to. Now the matrix that executes these transformations we always call lambda. So in this case we'll go lambda alpha, alpha prime, partial alpha, right? That equals partial alpha prime. So this is the transformation matrix of the basis. So now once we know that, we remember the rule of how these things transform, and the components transform in the opposite direction by index as the basis vectors. So ultimately what this means is that Q, alpha, beta, gamma, delta will transform with two inverse matrices, and it will be alpha prime alpha, and the inverse matrix beta prime beta. And then we know that the inverse matrix, the contravariant matrix, as it's called, will transform, say, gamma prime gamma dx gamma equals dx gamma prime, like that. And so this is the contravariant matrix. And this is the covariant transformation. I'm sorry, I should say the covariant transformation and the contravariant transformation. And this is, only reason this is covariant is anything that varies as the basis vectors of the underlying space V, that's we call covariant. If it transforms opposite of that, it's contravariant. I can spell contra better than that, right? Contravariant. And that is how the dual space transforms. So it's just a way of establishing whether it transforms like a dual basis vector or as a regular basis vector. So we know that the two contravariant indices transform contravariantly. Oops, I didn't put in the make that contravariant. Now the covariant indices transform covariantly. So I have to do lambda, and it's it'll be gamma prime and lambda delta prime, like that. And this is going to equal q alpha prime, beta prime, gamma prime, delta prime in the prime system. Where my notation for the prime and unprime system is obviously to put, that is the unprime system, and I put the prime on the alpha in the prime system. The alternatives notations is alpha, or A alpha, and then A hat beta might be the transformation into the new system, right? And in that case, you need to find a new symbol for each transformation. It's kind of a drag. This I find it much easier. But this index, by the way, it's in the prime system. It's unrelated. It's a different index, right? It sums over everything differently. It's only it's just an index in the prime basis, and we're calling it alpha just because it's a little bit easier. We're calling it alpha instead of, say, beta prime or something, because it's just a little easier to find indices when you do all of this. All right, so this is your regular tensor component transformation. The basis vectors are also transformed using the opposite of the reverse direction. So if this alpha index here is transforming this way with the contravariant transformation, I need a covariant transformation to transform the basis vector into the prime basis. And of course, this times this is the unit, right? Because these are inverses of each other. So you see that when I take this guy here and substitute it for that, and I make all of the appropriate transformations here, it's just a bunch of unit matrices all adding up, and so it really doesn't change anything. But if I split those unit matrices up and I divide it between this and this, what I effectively get is a coordinate change, and that's what I'm doing. So this is the standard tensor, the tensor change of basis. Now understand that the change of basis we're talking about is inside V, right? It's inside V. And so, you know, given the fact that we have this whole space-time going on, and there's a V at every point, I need a lambda, a covariant transformation at every single point, right? And it's got to be appropriate for every tangent space in the entire space-time, or in the words of the manifold, on the entire manifold, right? I've got this V, I've got that V, that's P, that's Q. You remember the picture, right? And of course, once I have the covariant transformation for every point, I automatically get the contravariant. It's just the inverse. And I can then transform any tensor from one basis to another. However, the basis that's been established at all these places is the coordinate basis, right? It's the coordinate basis, alpha, right? I put a coordinate basis at every point. So if I'm making a transformation at every point, I'm actually switching from one basis to another. I'm switching to, say, alpha prime. It equals A sub 0 plus B partial sub 1 plus C partial sub 2 plus D partial sub 3, right? The new basis is some linear product of the old basis, right? That's really what this does. That's what this actually says, right? This is shorthand for this. I should, I guess if I'm going to literally make it shorthand for this, I should say, say partial 0 prime, right? I'm saying, because this obviously is not a matrix multiplication, right? This here allows us to say all 4 at once. It allows us to say 0 prime at 1 prime, 2 prime, and partial 3 prime. All saying those all at once is what that is. One at a time is what this is. I'm kind of going into a pretty deep review here, actually. We're going way back into our stuff. I haven't even talked about the new stuff yet, but I guess it's not a problem. The reason is this is an important point. I need to remind everybody what the actual change of basis looks like for your standard tensor. If something, this is so strict, this is so important that, as I said in a previous lecture, this is how tensors are defined in physics, right? In physics that don't actually go into using these basis vectors, they define tensors as though the tensors are the components, right? As though tensors are tensor components. That's how general relativity almost always plays this game. They basically say tensors are these things, when they really mean they're the components of these things. They're the components of tensors. But mathematically, there's a lot of redundant information in writing this down. They realize, hey, you can do everything with just the components. So they're not crazy. It's just hard to understand. But then, in order to define what a tensor is, that's where it becomes tricky, because no longer is it multilinear maps, right? Now, it's an object that transforms this way, right? And that's what defines a tensor in your standard classic general relativity texts. Here you can define a tensor with the idea of multilinear maps, where these guys are all mappings. These two are defined as mappings, and these are understood, hey, they're mappings in a sort of a reverse sense. They map maps in a way. Anyway, but that's the nature of my presentation. I like to go all the way back to the beginning, because this, starting here, was always perplexing. But the point is if it doesn't transform like this, you can't call it a tensor. And now the next step is for me to show you that things that look like this, dx alpha wedge dx beta dot 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 wedge dx gamma, these things do not transform that way. They do not transform that way. And therefore they're not tensors, they're something else. Even though there's still elements of some tensor product space, right? If there's P of these guys, they're an element of this tensor product space. But because they're jammed into a subspace and they're given a component here that has the strict basis, alpha, beta, dot, 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 gamma, with these little lines, right? That component does not transform this way. So when the P form is written in this basis, with this strict component, that transformation rule doesn't apply, and we call it something else. We call it a tensor. Usually we call it a tensor density, although it can be something else, which we'll talk about in a moment. Okay, so where to next, right? So now we've reviewed what the tensor transformation property looks like. So I guess I need to explain or remind you what we're actually going to do here is, in order to study the transformation properties of these things, we got to study a transformation property in one given little space if we're given one gamma. But of course, or one lambda, one covariant transformation matrix. But if we take this covariant transformation matrix and make it a function of space-time, right, then we have one for every place in space-time. And now we can talk about the transformation of vector fields and tensor fields, because we're executing a covariant contravariant transformation everywhere. The other issue is we have this coordinate system, and our preferred basis is this coordinate basis. That's the one we like using. So what I need to show is that changing the coordinate system, if I change the coordinate system to say something, I don't know, something like this, right? So I change the coordinate system. The change of coordinate system will induce a new set of differential operators, right? And these new, I guess I only need this one. These new differential operators are referencing the new coordinate system. But it's still true that the new differential operators can always be written in terms of the old differential operators. And the way you do it is you have to find the appropriate covariant transformation matrix. So this coordinate change, this change of coordinates that I just talked about right here, this change of coordinates, once I execute that coordinate change, that gives me a covariant basis change. That's a function of spacetime, and that covariant basis change is what gives me the ability to transform tensor fields using this method. So let's talk about that. So where do we start? We start with, we are going to write down that, say, for example, I'm going to choose an example to work through, but the new coordinates, I'm going to use a two-dimensional system. The new coordinates, or I'm not going to say old and new, I'm going to say primed and unprimed. The prime coordinates, x0, is always given as a function of the unprimed coordinates. Right? So x1 prime is a function of, so these are the prime coordinates, and these are the unprimed coordinates. On this side, x0 prime represents a function on these of arguments with being the old coordinates. On this side, this number all by itself, that's just a real number. That's the new coordinate value given old coordinate values for the 0 prime coordinate. Same with the 1 prime. Here it's a function, here it's not. Right? And of course, once you have that, you've got to also have the other way, the inverse way. 0 of x0 prime, x1 prime, where the unprimed coordinates are functions of the prime coordinates. x1 prime always looks funny. It looks like x111 if I'm not careful. Okay, so once we have this thing, right, now I can define two matrices, and I will call those, I'll draw the matrices this way. I will draw the matrices as, say, dxi, partial xi, partial xi prime, like that. And that matrix will be defined as, obviously, partial 0 dx0 prime, partial x 0, partial x1 prime, partial x1, partial x0 prime, partial x1, partial x1 prime, like that. And then I will define another matrix, which is just the opposite, right? di prime, dxi. And that will be partial x0 prime, partial x0, partial x0 prime, partial x1, partial x1 prime, partial x0, partial x1 prime, partial x1. Let me erase this. Okay, got it. Now, I'm going to try to define my covariant matrix, right? My covariant matrix. So it really depends which system I'm moving into which system. But the covariant matrix, whatever it is the one that takes the basis vectors of the underlying space V, say call them alpha, and it transforms them into alpha prime, right? So So if I'm going to go from the unprimed system to the prime system, this is how I will define my covariant matrix. If I'm going from the prime system to the unprimed system, I define it this way, right? I have to be left over with the index that's correct, right? So I'm now going to call my covariant matrix depending on the way I want to make the transformation work, right? So it's going to be one of these two. It's going to be either this one or this one will be my covariant matrix. So which will it be? So I think for this example, I hope I can get this right. I want to use this one. I want to go from the unprimed to the primed system. I guess that's linguistically the most natural, right? So that means that if I'm going to go from the unprimed to the primed system, that means this guy here is going to equal lambda alpha alpha prime. Lambda, by the way, is obviously doing a bit of a double duty here, right? It's the covariant, or it's basically a matrix related to the transformation. It's also this P as in the exterior power, right? So, but of course these are unrelated ideas, right? So just, that's just the way some things go sometimes, right? All right, so this is going to be, this is our covariant transformation matrix, and then the other one will be the inverse, right? This will be the contravariant transformation matrix. And as a contravariant, it also goes from, you could think of it, so as a contravariant matrix, you can think of it as going from prime to it can be the covariant matrix going from prime to unprime, or the contravariant matrix going from unprime to prime, right? The point is whatever is the transformation that handles the basis vector of the underlying space, that is the covariant transformation matrix, right? That's the one that we call the covariant transformation matrix. Okay, so this is how, given this, if you supply this, you have to supply the coordinate transformation, right? You have to supply the rules of how the new coordinates look given the old coordinates. That's just some rule about switching your coordinates. You supply this, then these are continuous functions, right? These have got to be good functions. I can take the derivative of this thing with respect to x0, right? And that would be this expression right here. These are functions of spacetime. The derivatives are also going to be functions of spacetime. So these guys are going to be functions of spacetime, which is exactly what I wanted when I said I need to produce one of these guys at every spot in spacetime. So this is all working out. But I have to supply this, or I can't create these guys. But once I've created these guys, then any tensor I have, now I've got a way to transform the tensor itself. So so now I think we're in a position to start. We can do a test of this. We can test this on a very simple version of this, but also start showing why forms obey a different rule than this, which is really the point of all this, despite the fact that I'm kind of going on and on about this whole story. Okay, so let's pick a literal example, right? So the literal example we're going to use is we're going to have a space-time x unprimed, x1 unprimed. It's only going to be two-dimensional, right? We're going to go with just 2 dimensions. So each of these vector spaces V have just 2 dimensions to it. So I guess dimension of V equals 2, which makes perfect sense. If I have the coordinate basis, right, I only have d partial 0 and partial 1, and dx0 and dx1, or for completeness, d by dx0, partial by partial x1, right? These are the only 2 bases for the underlying vector space, for the tangent space. This is just the expansion of this. This is always a shorthand, by the way. This is always a shorthand. Okay, so with that in mind, hold on. So we're just going to deal with this very simple coordinate system, and we're going to change it to the prime coordinate system, right? So we're going to change it to x0 prime and x1 prime. And here's how the rule is going to be. We're going to say x0 prime equals the square root of x0 squared plus x1 squared. x1 prime equals the inverse tangent of x1 over x0. And then the other way, x0 is going to be x0 prime cosine x1 prime, and x1 equals x0 prime sine x1 prime. So that is our transformation equations. That is the transformation we're talking about. So we see that the prime coordinate is a function of the unprimed coordinate. Prime coordinate, function of the unprimed coordinates. Likewise, prime coordinate, unprimed coordinate, function of the prime coordinates in both cases. So this completely satisfies this structure right here. All right. So now the next step is to produce our covariant transformation matrix, right? We want the covariant one. Or we should produce them both. We should produce them both, all right? So in this case, let's start with this one. We'll start with partial x I partial x I prime, right? So that we've decided that. Well, actually, no. Let's do it the other way. Let's do it the other way. Partial xi prime, and then let's see if I can erase just that little thing. No, not going to do it. Partial xi prime, partial xi. Let's do that one. So we're actually working on. Hold on, let me make sure. Prime. So this will be the contravariant matrix. If we were going from unprimed to prime, we're now going to calculate the contravariant one. Why not, right? It doesn't really matter. You're going to need them both, right? To do this, you're going to need them both. So this guy, the first one is going to be the partial of xi prime 0. It's this function here. Oops. It's this function here, the derivative with respect to del 0, right there. So that's not going to be too hard to do. It's going to be x0 over 2 1/2 square root x0 squared plus x1 squared, like that. Let's see, and then so the derivative of the square root is minus. There's 1/2. So it's to the minus 1/2 power. So that puts it in the denominator. Right. All right. So this is x to the 1/2. So it's 1/2 minus 1. So it's minus 1. So you get that whole thing in the denominator. You multiply by 2x. But then it's 1/2 times this. So it's just this thing. Right. I think I got that. Well, I'll take a break when I'm done and double check everything. The same thing with respect to x1. X0 with respect to x1 is going to be the same thing. It's perfectly symmetrical, right? So x0 squared plus x1 squared, like that. And then we need the derivative of this guy with respect to x0. That'll go here. And the derivative of tangent, I happen to know, is 1 over 1 plus x squared. The derivative of tangent of x, or inverse tangent of x, d by dx equals 1 plus 1 over x squared. Useful fact, useful fact. And so, so what's that thing going to be? That thing's going to be 1 over 1 plus x1 over x0 squared times the derivative of that to the minus 1, so it's that to the minus 2, so it's x squared like that, right? But then times x1, which would end up there, so it becomes, is there a minus sign? I think there might be a minus sign. Let me think. x1 over x0 squared plus x1 squared. Let me check. I'm pretty sure there's a minus sign there, right? Because where would that have come in? It would have come in from. It would have come in from the derivative of the inside. It's minus 1. Yeah, there's a minus 1 from the derivative of this inside, right? Because that's going to be x1 times minus x over x0, minus 1 x0 to the minus 2. Yes, so there's going to be a minus sign. So draw a minus sign like that. And then let me just erase this. It's a little distracting. And then the last one is the same thing, but it's with the x1, you're taking the derivative with respect to x1 instead of x0, which should be a little easier. That one will be 1 over 1 plus x1 over x0 squared times x0, so I guess I can make that an x0 squared, and then I could pull this out and it's just that like that, and if that's down like that, if I made that x squared and I put another x0 here, then I can move that up here and I get an x0. So that's going to be x0 over x0 squared plus x1 squared. And this time there is no minus sign, right? There is no minus sign. Okay, I'm going to take a break for a second and just double check this. Okay, so that looks good actually. Huh, who knew? So so that's the contravariant. The contravariant transform. And now I want the covariant transform, which is the same process, but it should be a little bit easier for the derivatives to do, right? Because you're dealing with this kind of thing. So in that case, I could write partial xi prime like that, and then it's going to be this first thing, the 0 thing. It's going to be this guy taking the derivative with respect to 0 prime, right? That thing with respect to 0 prime, and that will be cosine x1 prime, and then the next one here will be that thing with respect to x1 prime, which is going to end up being wait a minute, no, it's that thing. Hold on. This is the zeros. This one here is the 0, 0. The 0th function with the 0 primes. Now I need the 0 function with the x1 prime, right? And so that is going to be x0 prime minus x0 prime sine x1 prime, right? And then I need the 1 function with respect to 0, so that's easy. That's sine of x1 prime. And then I need the 1 function with respect to the 1 function, which is, well, that's no sign change, x0 prime cosine x1 prime, like that. Okay? So that is the inverse transformation matrix. All right, so now with those two things in mind, now I have both, right? So this is going to be what we call lambda inverse I prime, I prime I, and this is going to be lambda I prime. All right, so we've We've just created those two things. And notice they're functions of space-time, just like I promised. This is a function of x, and this is, well, see the problem here, this is a function of x prime, so that's not good. We need everything in the function of x. That's right. So I've got to actually swap these variables out for x. So that's actually not going to be too easy. So let me, so right now what I've got is I've got lambda I prime as a function of the prime coordinates, right? I guess the way I should write that is x alpha prime to be consistent with my notation. Hold on. To be consistent with my notation, I should write x alpha prime like that. But I really want that to be lambda I prime as a function of x alpha. But this is easy because now all I have to do is substitute in here these guys, right? I mean, I know x1 in terms of these two. So I end up with the cosine of the inverse tangent of x1, x0, and I end up with let's see, x0 prime. Oh, it's that thing. Yeah, I'm gonna do this. I'm gonna write box for x0 squared plus x1 squared. I'm going to write box, right? So I get minus square root box times the sine of the inverse tangent x1, x0. And then this other one here is just the sine of the inverse tangent of x1, x0. And this one here is minus the square root of box times the minus the square root of box. Yeah, I think minus the square root of box times the cosine of the inverse tangent x1, x0. Right. I'm going to pause just to double check that. Okay, yeah, there's no negative sign here, right? It's just square root box cosine. But you can work a little trigonometry here, and this can be simplified, right? I mean, I'm sketching it out because you know, if we treat this as, say, x0 and x1, the inverse tangent is this angle, and the cosine of that angle, if that's square root box, is going to be x0 over square root box. The sine of that angle, so that's the cosine, the sine is going to equal x1 over square root box. So this whole thing is going to be x0 over square root box. This is going to be x1 over square root box. And then this guy here is going to be x1 over square root box times minus square root box. So I think that just is minus x1. And likewise the one below it is x0. x1. So this equals our covariant transformation matrix expressed in the unprimed coordinate system. Okay. So good. Now we've got a lot of stuff. We've got our contravariant matrix expressed in the unprimed system, and we've got our covariant transformation matrix expressed in the unprimed system. So with that, we can now transform from the unprimed to the primed system, meaning we can execute this process, right? Because this process, you know, this is what we're looking for: the component of alpha, the component in the value of a component in the prime system. I know the value of the components in the unprimed system because presumably I'm transforming a tensor that I know the value of, and I needed to know these things, right? And but I need to know these things at the same point as this thing, right? So I know the value of this, because remember, this alpha, beta, gamma, delta is a function of space-time in the unprimed system. So that's why I went to the trouble of calculating this guy in the unprimed system, because I need to know this guy at the same point. And the only way I can do that is if I have this as a function of the same spacetime. So that's kind of why I went to all the trouble of calculating this guy as opposed to leaving it here, or leaving it here actually, right? Leaving it here. So here goes to here. This would work, right? I didn't have to go beyond this, I guess, but a little trigonometry, and you can kind of turn it into, instead of trigonometric transcendental functions and their inverses, you just got some sort of algebraic rational functions. Okay, so now let's use this to actually transform a real tensor. And the one we're going to choose is going to exemplify what we're trying to show here. We are going to actually transform the following tensor. We're going to transform the tensor Q, where Q equals dx0 tensor product dx1 minus dx1 tensor product dx0. Right, that's the tensor we're going to transform. First of all, it's a totally normal tensor, and it is a member of 0 to v. Therefore, the rule we talked about back here, this rule right here, applies. Right? We just get rid of these two indices. Right? Get rid of these two indices and get rid of these two. So I'll just do it now. We get rid of those two. We get rid of those two, and all you have is now you have a 0-2 tensor. And all I need is these two matrices here, and I can find its components in another basis. Guaranteed to work every single time, right? If you're dealing with a tensor. But are we dealing with a tensor? Yeah, we're dealing with a tensor, right? This is part of the tensor. This is the basis of this tensor product space. Now there are two other bases here that we're not using, right? We're not using this one, and we're not using these two other basis vectors, and we're not using this one. But that's all the basis vectors in here, right? Because the dimension of T0 to V equals the dimension of V to the second power, right? Because we've got two of them, which is 4. Because remember, we agreed somewhere back here, we agreed that we were dealing with a dimension 2 space. And that's for simplicity, right? That's to keep these guys small, right? Doing it any smaller and it doesn't really exemplify anything, right? A one-dimensional space is very uninteresting. A three-dimensional space is probably where we should be, but that would be just a little more than, this is already running really long, right? So, we don't use these because obviously Q is antisymmetric. But that's just saying that Q00 equals 0, Q11 equals 0, Q01 equals 1, and Q10 equals minus 1, right? That's our tensor. And these are the 4 components of that tensor, which is an element of this tensor product space. So we can transform this using the regular rule right here. Well, the regular rule is with these things crossed out, right? Because I'm talking about a 0-2 tensor now, right? Okay, so let's actually do that. So back to black. So how does this work? So we have Q alpha beta dx alpha tensor product dx beta. Oh, I guess I should say, by the way, obviously I've chosen this because I know it is the same as dx0 wedge dx1, right? Right, and that is the basis of the second exterior power. That's the one basis element of the second exterior power, because remember, you've got to choose dimensionality of V. Dimensionality of V choose 2, which equals 1. So that's the dimensionality of this thing. The dimensionality of this equals that. So here I'm looking at something that's got 4 dimensions to it, right? But the components have eliminated 2, so it looks like it has 2 dimensions to it. But since this component is just equal to the opposite of this component, it actually turns out it has 1 dimension to it. And So we're going to make some comparisons at the end about if I had written it this way, right, with a single dimension instead of two dimensions, how would that single object have transformed? And it doesn't transform, as I keep saying. It doesn't transform this way. It has its own rule. Okay, anyway, but to show that all of this stuff is the same, I take this and I'm going to actually, I'm looking for the prime values. I'm looking for this thing. And I know that by the tensor transformation rules, I know this is going to equal Q, let's see, how will I write this down? Say Qij. These are covariant components, so I use the covariant transformation matrices, J prime, right? And then I have dx, say K, tensor product dxl, like that. But this guy is going to transform contravariantly, right? So I do this, K, well, I guess I got to do it, oops. All right, so this should have been an alpha, and this should have been a, damn it, sorry. So this should be an alpha, and this should be a gamma, and this should be an alpha prime, and then this is another contravariant matrix, and it should be a gamma prime, like that. And notice right away you should be able to see this is unity, right? This guy here, hold on, no. Wait a minute. I've got this, see, I'm checking myself. I'm glad I checked because I found a mistake, right? These guys should be, they should all be matrix products that add up to unity, right? You know, the transformation of this I component, see, this alpha here is supposed to be I. So yeah, I just totally messed this up, guys. Why would you even, this is embarrassing. I'm going to have to rewrite it. Sorry, I messed this up, right? This has got to be the same thing as over there, right? So this has got to be alpha, beta, lambda, alpha prime, transformation matrix, beta prime, and then I need the contravariant one for, this is dx alpha, so I need alpha prime, transform lambda inverse, beta prime, beta dx beta. That's the way to do it. Sorry. So now you can see this matrix here multiplied by this matrix here, that is the unit matrix. That's 1. And this matrix here times that matrix there, that's 1 also. Wait a minute. Doggone it. I've noticed that these are dummy indices here, right? These should be these are dummy indices here also, right? But it's bad to choose these dummy indices to be the same as those dummy indices. That's kind of confusing, and in the end you get something weird with the way these matrices are multiplied together, because this should be different from this for it to become this sort of unit matrix. So again, I have to make a change. These dummies, sometimes, the reason I don't just redo it, by the way, the reason I don't stop and erase it and redo it and say, oh, the people following, they're going to have trouble, is because my mistakes, see, I just rewrote the same damn mistakes. My mistakes are, they're part of my process, and understanding my mistakes actually is edifying, right? I mean, following the errors I make, I mean, it slows things down, I admit that, but sometimes correcting errors is sort of where you see things happen. That's where a lot of times that's where a lot of educational money is in. That's tracking down mistakes, either my own or somebody else's, was an important part of my learning. So that's why I'm not cleaning this up. I mean, I could just do typewritten notes and present it step by step, typewritten. And there are some other places that do that, but those are good. They're good. It's just not quite my style. It is admittedly getting long, though. Okay, so this transformation, this is the transformation that we need. So now we can just make all these substitutions. So in this particular case, the way I would do it is first thing I do is I take these things and I just change them. That becomes dx alpha prime tensor product dx beta prime, right? That transformation is done. So now I just have to worry about this part of the transformation. I also don't have to worry about the 0, 0 and the 1, 1 term. So now I'm going to just sum over alpha beta with the terms that are actually left. And there will be, let's see, there'll be quite a bunch of them. So what I'll do is I'll just write down a few. Well, let's see. All right, so let's just do it sort of. How do I say so? Some step by step. Say I do it with q 0, 1 like this. That's going to be lambda 0, lambda 1, alpha prime, beta prime. Right? So that's one of the alpha beta combinations. To that, I would have to add q1, 0, lambda 1 alpha prime, lambda 2 beta prime, kind of like that. And let's see. And the basis vector here, well, of course, we know what the basis vector here, it's this, right? It's this term here times that. So I guess I would put this in some kind of brackets, and then I would go dx alpha prime, tensor product dx beta prime, like that. So now I have to calculate this term by term, choosing x alpha prime and x beta prime. So for example, I could choose, let's say, q01 lambda 0, 0 prime lambda 1, 0 prime. Then that term would go to dx0 prime dx1 prime, right? And that would also be plus, I think there's a 1, 0 involved in that as well. Yeah, so there would be a q1. Well, let's stick with the q00s. Let me just stick with the q00s, or the q01. So the q01 prime, there's this one, and then there's q01 of lambda 0. I guess the next one would be 0 prime lambda 1, 1 prime dx 0 prime tensor product dx 1 prime. Actually, I'm sorry. So look, this is a 0 here, that's a 0 here. These align with these, so this is supposed to be a 0 here. And of course, that term goes to 0 because we know that there is not so fast, not so fast, not so fast. So that term exists. Remember, we're doing a transformation. We don't know up in advance. We don't know what is going to be left over in in the new basis. We don't know. So so we can't say for sure what's going to be there or not, just because this term has no component in the x coordinate system. Just because it's 0, that doesn't necessarily mean that something won't pop up in a different coordinate system, right? That's the whole point. Coordinate components get all wacky. They change like crazy when you switch coordinate systems. They're very fickle. Okay, so anyway, that's the 0, 0. That's the 0, 1 term. So what's next? Then there's Q. Oops. There's Q0, 1 lambda 0, 1 prime lambda 1 0 prime dx 1 prime tensor product dx 0 prime, right? That's 1 prime 0, and then there's Q0, 1 lambda 0 1 prime lambda 1 1 prime dx 1 prime tensor product dx 1 prime. So there's those guys. Then there's the equivalent batch where I go to the 1 0 term. That's this term here, right? I've just expanded this term, right? All of this is an expansion of this term here, right? Now I need an expansion of this term here, right? And that's going to be the following guys. It'll be Q1 0 lambda 1 lambda 0, and then I go 0 prime 0 prime, right? And that will be dx 0 prime dx 0 prime, then Q 1 0 lambda 1 lambda 0 0 prime 1 prime dx 0 prime dx 1 prime, and then Q 1 0 lambda 0 lambda 0. What would be next? I guess it would be 1 prime 0 prime dx 1 prime tensor product dx 0 prime, and then Q 1 0 lambda 0 1 prime lambda. I'm sorry, this should be a 1. It should be a 1 0 1 prime. Let me clean that up a bit. 1 1, because remember the indices up here, right? These indices, well, these indices here match those up there. These indices here match these over here, right? And so this last one gets what? dx1 prime tensor product dx1 prime, like that. Okay, so now looking at all of these things, we know that Q is antisymmetric. So we know that Q01 equals minus Q10. We know that because that's what we stipulated. Where did we stipulate that? I guess we stipulated that, well, it's right here. It's right here in the definition, right? That's Q01 and that's Q10, right here. So we know that these are antisymmetric. So because of that, we can do some cancellations, right? We can cancel this term here with this term here, right? Because all that is this switched. But this is also switched, and this sign changes. So this guy cancels with this guy. And likewise, we have a switch here. The 1 1 0 1 prime should be canceling with the 1 1 0 1 prime, where this and this are switched, so that cancels. So that goes away. So that eliminates 4 of them. And then we have 4 left. We have this, 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 and this. And so now we literally need to take the matrix elements of these guys here. Those matrix elements will come from this matrix right here. right, the one that we calculated, those matrix elements will stick right in here, and that will be, and then we'll we'll add this one, the x0 prime x1 to this one, because they are terms of the same basis vector, and that sum will be the component in of that basis vector in the new system. So let's look at this. What is this one? This is 0, 0, 1 times 1, 1. So Q01 is, so let's add that up. I'll do it in blue. Right, in blue. So the 0, 0, 1, 1, I'm going over here, and the 0, 0 times the 1, 1 is x0. That is a 0 there, right? It'll be x0 squared over the square root of the box, right? So what do we get? We get x0 squared over the square root of the box, and then this guy is this guy here, right? This guy here in this lower left corner, it's the 1, 0 prime, 0, 1 prime, right? It's for the same basis vector as this one. So the 1, 0 prime for the 0, 1 prime. Let's see if I can remember. So the 1, 0 prime is this, and the 0, 1 prime is this. So that's minus x1 squared over root box, right? So it's minus x1 squared over root box. But remember, it's times 1, 0, right? But we've decided that 1, 0 is negative 1, right? Which you can see from right here. That's 1, 0. That's that negative 1. So that this minus sign right here, that guy becomes a plus sign, right? And then that is dx0 prime tensor product dx1 prime. And so that's it. We've just transformed the component. I guess I meant to do this all in blue. We've just transformed the component. We now know, so this component here, this thing in blue, let me erase this so it doesn't confuse anybody. This thing in blue, that equals Q0 prime 1 prime. That's the transformation. In fact, it's simpler than that, right? That thing actually equals, when you remember that box is x0 squared plus x1 squared, you've got square root box, you've got box on top and square root box on the bottom, so it actually equals square root box, right? So that's what this component is. So we've calculated one of the two transformations. So let's see, let's cross that off in blue. We've done that one. And then the other one, right, is 0, 0 prime, 1, 1 prime. Wait a minute. I think I crossed the wrong box. Undo. See, I got to cross off. Oops, I've got to cross off this one and this one, right? So now I need this one here. So I need 0, 1 prime, 1, 0 prime. So we go back here. 0, 1 prime is minus x1, and 1, 0 prime is this. So it's minus x1 squared over root box. So this one is minus x1 squared over root box. And then I have to add that to this guy here, which is 1, 1 prime, 0, 0 prime, which I think we already did. 1, 1 prime is x0, yeah, it's x0 squared over root box plus x0 squared over root box. But the x0 squared over root box, don't forget I've got this 1, 0 here, which is a negative 1. So that changes that plus sign to a minus sign. So I get this, and then that is the component of dx1 prime dx 0 prime. So it's q 1 prime 0 prime equals, and then when you do the algebra on this, you get minus square root box, right? Minus root box. Phew. So after all that, we end up with this. We've now figured out what this is, and what that is it's going to be q alpha prime beta prime dx alpha prime tensor product dx beta prime is going to equal square root box dx 0 prime tensor product dx 1 prime minus square root box dx 1 prime tensor product dx 0 prime. Okay, so there you have it. That is the transform. We finally transformed. That is the transformation of, that is the transform value of dx 0 wedge dx1 minus dx1, not wedge, tensor product dx0. This is in the unprimed system. I transform it using this coordinate change. Remember, everything was driven by this coordinate change, right? That coordinate change led to this covariant matrix, and what we're transforming is an entirely covariant tensor. So I only needed to transform the components. I only needed the covariant matrix, right? If this was some mixed tensor, I would have needed others. But I'm demonstrating this on purely antisymmetric covariant matrix, and so using that, I generated this formula. I guess I did use the contravariant matrix, but only symbolically, because we know that that just transforms into these guys here. I don't really care about the linear combination in the old matrix that make these up, but I could calculate that. If I actually ran this through, if I actually went back here to this this matrix here, if I took this matrix, this inverse, the contravariant matrix, if I took that and I actually did this, executed this term by term, I would end up having an expression of this one form in terms of the one form basis in the other coordinate system. But I don't really need that. I just need to symbolically do the transition. So all I'm left with is transforming the coefficients. And by the way, that's exactly why general relativity textbooks throw this away, is because this is sort of this half is sort of a symbolic exercise. All the money is really here, right? Now I guess we could have done something slightly different, and we could have left the components the same and just thrown them into the prime system and changed the basis vectors around, and you would carry these long strings of basis vectors together. That would have been a mess. But doing it this way, all you really do is all you need to do is carry this around, and if you understand how these transform alone, you kind of don't need this, right? It doesn't help you understand it any better, but once you do understand it, going back to this, you'll inevitably go back to this anyway. Or you'll go back to the system that has only components and doesn't carry around basis vectors. But what was I saying? So this thing transformed is this thing here, which now allows us to make the crucial observation that that equals the square root of box times dx0 wedge dx1 prime, right? Wedge. So I write this side as dx0 wedge dx1. It transforms into this thing here. And then you need to note the crucial properties. This thing here, right? This thing here is really what the sort of the story is, because I want to talk about the transformation of the same tensor when it's written in this basis. And in that basis, what would it be? Well, there's only one. So in the strict basis, it would be 0, 1. In the strict basis, dx0 wedge dx1. Now notice this is one-dimensional. This is the only component that exists, right? Because we're dealing with two dimensions, and a 2 vector in 2 dimensions, right? So the number of dimensions is the number of dimensions, 2, and it's a 2 vector, 2, right? So boom, that's it, 2 vectors in 2 dimensions. There's only 1 dimension here. So we're asking, how does this thing, this single thing, transform? Notice our other question had to be, how do these 2 things transform, right? Because there were 2 components. How do they transform? In fact, we really need to know is how all 4 of them transform. But ultimately, the question is, we have these 2 components here that are non-zero, and here we have 1 component. Here we can only have 1 component, by the way. It's not like we're missing the 1, 0 version, right? In strict components, there is no 1, 0. If we had a 1, 0 component, it would be on top of a dx1 wedge dx0, but that just equals minus dx0 wedge dx1. So these aren't linearly independent basis vectors, right? So if I had a 1, 0, I would just flip this around, change the sign of this thing, and add it to that. And I would be back in with 1 component again. So that's really important to understand. We're dealing with 1 dimension here. But I guess I should point out about this. When you go back here, right, when you go back and look at this, you'll notice that the transformation of the Q01 component, you go through every alpha prime and beta prime, which is what ends up on the basis vector. You can generate, it's conceivable that these matrices would have been such that the alpha prime equals 0 and the beta prime equals 0 compart. That is, this part right here, right? It is possible that that would be non-zero, right? The reason it's 0 here is this canceled out exactly with this, right? Because this was the opposite of that. If this was not an anti-symmetric tensor, then this cancellation would not have happened, and a 0, 0 component would have appeared where there was none before, right? There was no 0, 0 component in the unprimed system, but the only reason there's no 0, 0 component in the prime system is because of this very precise cancellation between these two. And that cancellation was entirely driven by the fact that this and this are opposite sign, and because that opposite sign change wipes them out. So the point is that's why these dimensions don't reappear in this particular problem. But they would reappear in general for a normal tensor, a tensor that's not antisymmetric. Now, let me finish erasing this. Okay, so ultimately we know that the value of this in the unprimed basis, that equaled 1. The value of that thing in the prime basis we now know is the square root of box. I guess box is, at this point, I should write down x0 squared plus x1 squared. Right? So it's a value at every point in space-time, dx0 wedge dx1 prime. This is a number that's calculated in the old coordinates, by the way, but it actually equals the determinant of the covariant matrix, right? The determinant of the covariant matrix, lambda. And you can see that by going here and looking at this matrix here. You get x0 squared over box minus a negative x1 squared, so it's plus x1 squared over box. So you have x0 squared plus x1 squared over square root of box, which is just square root of box in the numerator. So this is the covariant matrix. Its determinant is what lands here. And so the result is that Q01 went to Q01 times the determinant of the transformation matrix. That's how the 0, 1 component transformed by multiplying that, and that equaled Q0 prime 1 prime. So the transformation of the component when written in this basis is the old component multiplied by the determinant of the transformation matrix. Now, be careful, this rule here only works as I've just drawn it for the case when you're dealing with ultimately a one-dimensional space of forms, when you're dealing with this n over n situation, right? And I specially designed it that way, right? We specially designed it. We have two dimensions, two-dimensional space-time, which is a two-dimensional vector space everywhere, and we're looking at the transformation of a two-form, right? In not only any two-form, but this particular two-form, well, any two-form, it would have worked for any two-form because there's really only one dimension of all two forms. All two forms look like this, right? The only difference between two forms is the factor in front. It's one-dimensional vector space, right? They're all related by some constant factor. And if you transform the coordinate system, that leading factor changes due to just the coordinate change by the determinant of the well, it's essentially the determinant of the Jacobian of the transformation, but it's the determinant of the covariant transformation. So that is how this works for that one particular case. If I had done this where I was using three-dimensional space, right? You know, some, I guess, lines coming out, right? Something like that. Three-dimensional space, it would have still worked, right? The transformation we would have done x0 prime, x1 prime, x2 prime equals some function of the old coordinates x0, x1, x2 is some function, some function. I guess that would be the 0 function, the 1 function, x0, x1, x2. I would have done the same thing. I would have formed the same partial derivative matrices as I did before, right? And those, I would have chosen the covariant one, I would have chosen the contravariant one, depending on which way my coordinate transformation is going. I would have calculated a lambda, I would have calculated a lambda inverse, and in the end, I would get this rule for three forms, right? Three forms, because all three forms would have been dx0 wedge, dx1 wedge, dx2 with some constant. Every three form is just a different by a constant, right? And if I switch to the prime, it would be, I'll call that constant c, times the determinant of the covariant matrix, right? That would always have happened. So that is the story of how this works in that particular case. And the things to understand is it's the same darn tensor, right? It's this tensor here written in a basis appropriate for the tensor product space 0, 2, v. It's the same tensor as this thing written in the basis appropriate for exterior power 2, v. But the transformation rule of the single component is this transformation rule, whereas the transformation rule of the two components here, this one and this one, that obeys this transformation rule, right? But in some sense, everything is the same. It's just a matter of what basis we choose. So in the next lecture, I'm going to talk about this in more generality because, remember, I'm only dealing right now with the case of P forms in where P equals the dimensionality of the underlying space, right? That's where this rule applies. This rule does not apply for the case of n-1 forms, right? n-1, right? By the way, that is going to equal n, right? Because it's n factorial over n-1 factorial times n minus n-1 factorial, which is 1 factorial. So that ends up being equal to n, right? So in the n-dimensional case, you have a different rule, right? This is not the rule for the circumstance where you're looking at forms that live in this space, right? And there's a different rule for forms that live in that space, right? So we've got to understand it for this space in particular, and then a general rule for every space. And that is our next lecture. Okay, sorry about this lecture being so long, but next lecture will probably be just as bad.